Here we're going to study the behavior of a system that we previously derived the state space model for. So previously we saw that this 2 degree of freedom system with 2 masses and 1 input, we have a state space model. We have the A, the B, the C, and the D matrices from before. So just refresh ourselves on what those looked like of their sizes and their values. So we are going to see what happens to the system if we change the input into the system, if we change the masses, the spring constants, the damping coefficient, of how now these 2 degree of freedoms are going to behave with initial conditions and without initial conditions. As we saw in the last numerical example, where we want to start is by defining the state equation for this system. So we're going to use that A and that B matrix along with how we defined our input vector and our state vector and create a function. So here, the job of the function is just going to be at the end, define x dot. And in this system, x dot is going to be 4 by 1. It will be x1 dot, x2 dot, x3 dot, x4 dot. And the way that ODE 4.5 is going to work, we have to make this a column vector. So for this example, I'm going to define my parameters within this function, the m values, the k values, the b value, and I'll just start arbitrarily picking 5 and 2 for the masses, 3 and 2 for the spring constants, and 6 for the damping coefficient, all in base units here. And we'll change those, we'll see how the behavior changes, but we're just exploring in this example. We don't have a specific system that we are trying to study the behavior of, but this general system with parameters for the masses, the spring constant, the damping coefficient. And then I will define my u, my input, as an inline or an anonymous function. I'll start with it just being 0 and see what happens if I change it to a step function or a sine function later, just see how the behavior of our system changes. But for now, just 0. We're only going to start with non-zero initial conditions and see what happens. Then I define my A matrix, as I previously found in the modeling step when I went through the state space model. So this 4 by 4 A matrix is coming from the modeling, and the B vector in this case, or B matrix more generally, coming from how the input is put onto the system. So here we have a 4 by 1 vector. Then because it's a linear system, I know that my x dot is going to be ax plus b times u. And in this case, u is again this anonymous function or inline function, so it has to take the current time. So the basic structure is the same as what we saw in the previous numerical example. We define the A and the B matrices and we put it together, and that's again the only job of this function is to define x dot at every time, and for every current state, it's going to tell us what are the derivatives of our state variables. So with this function in mind, let's see what the driver file is going to do. This too is going to look a lot like that previous example for the 1DOF system. I'm going to call ODE 4.5, and now I'm going to use this function that I was just talking about. So ODE 2a that takes arguments t and x. And again, I'm going to tell ODE 4.5 that the time is going to be called t and the state is going to be called x. And that matches here what I am calling those arguments in my state equation file. In this example, I am going to run it from 0 seconds to 150 seconds. We'll see that, at least for our first examples, that will give us enough time to see anything interesting happening. I'm not defining what timestamps to use in between. I will let ODE 4.5 determine that. I just want a beginning and an end. And over here, I have my initial conditions. I have 4 state variables, so I have to tell it the initial condition on each of them. Just for this example, I'm going to assign x1 to have an initial condition of 0.2 in base units, I guess meters in this one, and I'll leave the rest zeros. But again, I need, even if they're 0, to define the initial condition or the values at my start time, in this case 0, I have to define all 4 of them. In this example, I'm tracking the 2 degrees of freedom, which are y and z. So c is going to be these 2 rows by 4 columns. I have 2 outputs, y and z, and I have 4 state variables, so that gives me 4 columns. And I define my d, which is just the zeros matrix or a zeros vector here. I define it Because it's zeros, I'm not going to worry about it in this line 13. I don't need to worry about how the inputs are going to directly influence my observables or my outputs. But in general, I could have a D and a U over here as well. I'm just not including it here because D is a zero vector. So C is going to be multiplied by X prime or X transpose in MATLAB, and I'm going to transpose the whole thing. Again, this is because of how X is coming out of ODE 4.5. It's coming out as column vectors, and really here for the multiplication to be correct, the way C is defined, I need to multiply it by row vectors. But then the result I want back as column vectors. So I'll transpose that, and that will be Y. All right, so that was, again, very similar to the previous example. So let's start playing around with this and see what happens as I vary different aspects of the system, be it initial conditions, inputs, parameters, and how it's going to change. So in this case, let me just start here. I'm going to have a non-zero initial condition, but I'm going to have no forcing in the system, and let's see how the system behaves under those circumstances. So I'm going to plot all my results down here for just these two displacements. All right, so running this through, I get here, I'll make it a little bit bigger so we can see what's happening. The Z and the Y, so notice, let me track Z, has that non-zero initial condition of 0.2. By how I define my order of state variables, I'm making initial position of Z 0.2, but the initial position on the Y is going to still be 0. So they start at those initial conditions, both with 0 velocity. And we see that once we let go, we put our system into motion just under those initial conditions, that they are both oscillating at seemingly about the same frequency. We're going to investigate more about that frequency when we get to Unit 2 and more properly look at our analysis section of how is it oscillating under these conditions. And we see that they do have these different amplitudes. Z has a larger amplitude than Y does, but over time, the energy, these oscillations are going to dissipate, and eventually both masses are going to return to their equilibrium state. So 0 for Z and 0 for Y. So energy is being dissipated by the system via the damper, and eventually we get back to equilibrium. So let's just see what happens under slightly different initial conditions. I'll give it a larger initial condition on Z. And actually it looks basically the same, just scaled differently in the Y-axis. And still we are eventually going to our equilibrium point of 0. And let's just see what happens here. I'll give this 0.2. Let me make the other position initially negative 0.2. So remember, from how we defined our state variables, x1 was Z, x2 was Z dot, the velocity, x3 was Y, x4 is Y dot. So now we see our initial conditions clearly are different. Y is starting down here at negative 0.2, and Z is starting up here at about, get closer, there it is, positive 0.2. And actually initially we have a little bit of odd behavior, I would say, in Z, where it kind of comes closer to 0, away from 0. But then kind of after that, the behavior is fairly similar to what we saw before, where they're oscillating more or less together. They are slightly what we would call out of phase, which we'll talk about later, but roughly at that same frequency, at least by I. So these are, let me put this back to 0. Now let's look at what happens here as I change some of the system parameters. So let me give this more damping. Well, actually, let me run just up to defining A under these parameters. Let's see what happens. So if I look, kind of like I looked at before, let's look at the eigenvalues of A. And we notice here the eigenvalues are all in the left half plane. We actually have two unique real eigenvalues, and we have a complex conjugate pair of eigenvalues. And we saw in this case that we did observe oscillations in the system when we gave it an initial condition, no forcing, just an initial condition, and let go of it. What happens if we increase the damping? So let's pump it up to 15 and see how redefine A with this new B. And let's look at the eigenvalues of A. In this case, they are actually both we still have left half plane. They are both distinct in the real part, and then again complex conjugates for the complex part. So let's just see what happens. Let's turn this damping up, put it up to 15, and let's just see what changes when I run this section. All right, so turning it up, we see the oscillations are different than what we saw the first time where we had a different damping coefficient, but we still do have these oscillations happening. Let's turn this up quite a bit. Let's go to 45 just to see what happens differently in our system. We definitely see a different behavior here when we go all the way up to the 45 in the damping. So Z is fairly quickly coming down near its equilibrium point. Eventually it will die off. It's going to probably take longer. Let's just run this for longer to see what happens eventually. All right, so running it for longer, these oscillations are getting smaller as we go through, but it's taking a little bit longer for them to get really close to zero. Let me set this back to just 120 or 150 for seeing these differences, and I'll set this back down around 6. Okay, let me get out of the realm of what we would call an autonomous system, where we have initial conditions but non-zero initial conditions but no forcing, to what we're going to spend more time looking at in this course, which is forced systems with zero initial conditions. So this is what we'll get into as we talk about first and second order systems going forward in the second unit. So zero initial conditions now. If I do it as it is with no forcing and no initial conditions, well, it's not going to be interesting at all. Nothing's happening. Everything starts at 0 and it never wavers from 0. So let me put on here a Heaviside function. So I'll uncomment this. So I'm going to give it a unit step input that starts at 3 seconds. So it should do nothing, and then suddenly at 3 seconds, I'm applying a step input for U, and let's see how the system responds to that. All right, so notice the 3 seconds is not very long. Nothing is happening. I suddenly apply that unit force for U1, and now the system is behaving and responding to that. Kind of it looks like what happened when we gave it a non-zero initial condition, but it is different, where it's going to oscillate, and then eventually that energy we added into the system is going to be dissipated. But unlike giving it a non-zero initial condition and it going back to its equilibrium point, because I'm applying a step input, I'm giving it that kind of permanent force acting on it, eventually my system is going to go to a new equilibrium point, more or less. So it's not really the equilibrium point. That hasn't changed in the system, but it's now hovering. Both masses are now at about, well, it looks like 0.5 meters going forward, as long as that force remains on for U1. And this is going to get into step inputs. We're going to look at those a lot as we go forward in first order systems, second order systems. This actually is a fourth order system. It's more complicated than really what we're going to be studying more in depth, but it's good to just kind of explore this behavior. And let's just see, because we'll look at this also going forward. What if I give it a unit sine function? So the simple sinusoid acting for U1. How does the system respond to that? So if we look at this, and we'll be looking at this also in Unit 2, what happens if we give it just a simple sine or a simple cosine function? We're going to see kind of similar behaviors. Well, kind of both z and y start to oscillate when I have that sine input acting for U1. And it takes until around, let's say, somewhere here, around 100 seconds or so until kind of we get this definitely repeating pattern happening. Maybe a little bit before that, but definitely around 100 seconds, this repeating pattern for y and for z happening. Let's ignore the first 100 seconds for now. That's what we're going to be calling the transient phase when we have this periodic input, this sine or a cosine input. We'll look at the transient phase more in vibrations in the follow-up course to this. We're in this course going to look at what happens once we reach steady state, around 100 seconds. Y and Z are both oscillating at the same frequency, it looks at least visually, but with slightly different amplitudes in this. And if I zoom in a little bit on what's happening during this steady state phase, We see again different amplitudes on z and y. It turns out it will be the same frequency, and that also turns out it will be the same frequency as the input, which we'll talk about later, and they are what we say slightly out of phase. The peaks of the two are not occurring at the same time, but same frequency, but just z is kind of right shifted relative to y, at least looking at the picture here. So this was just some exploration of a little bit of changing the parameters, changing the inputs into the system, but the model is really the same each time. A and B are still defined the same way. Maybe they have to be recalculated when we change the parameters, at least for the M's, the K's, the B's. But what we select for U doesn't change what A and B are. It does certainly change down here what X dot is, depending on what U is. But the model we built in this Unit 1 section is robust because it exists independent of the specific input that we're putting into the system. We're just saying there is an input acting in the system. We later define it in these examples as 0 or a step function or a sine function. And then we see what our observables are. And we can also change the parameters because we initially derived our model completely algebraically. So it's pretty quick, it's pretty simple to change a couple parameters and resimulate the system, and we can see how the system behaves under a lot of different conditions, different initial conditions, and so on.